So today we're working through the homework. Practice problems 2 and 3. Extra practice problems 1 through 3. And Sydney, you have a penetrating voice. Right. Who wants to do 2? Sure. Okay, let me see who seems to be the most bored and distracted in the room. Pardon? It's Tuesday, April 18th at 8:18 a.m. Eastern Standard Time. I'm sorry, can I help you with your confusion? Yeah, and I said, does anybody want to do it? And then I said, I'm looking for who seems the most distracted or bored. And then Kiefer changed his disposition. So I couldn't throw the marker at him. So I was looking for who was second. But anybody want to be teacher for a problem? I'll have to get, next year I'll do that. I'll have a bucket with all the students' names in it. Or make it more interesting. I'll have your student ID number in it, and you got to remember what your student ID number is, so I can just pull the ID number. So when I send emails and letters home and I refer to you by your ID number, I don't get calls from all the parents going, who? Okay. Yeah. I don't mean to be mocking, but okay. Edit point. Okay, there we go. Practice problem number 2. I just want to encourage you on every one of these problems. This is just process, but it's recommendation, okay? Gas law problems or gas problems other than the kind experienced by those gentlemen. Just go ahead and write these on your paper every time. You may not need it. If you get to the place where you can scan ahead on the problem and know what you do and don't need, just settle for that. But if in doubt, just go ahead and write that on your paper every time. As a matter of fact, when I was taking chemistry, I used to just have a block. I made copies of pages, used 3-ring binders. When we were doing gas problems, I made sheets that had these on them, and I just copied those sheets, then 3-hole punched them, put them in my binder. So every time I came to a gas law problem, those are already up there on the page. I didn't have to write them again. And then go through the problem, the word problem, extract the data that you need to solve the problem. So number 2 says, a bacterial culture, no, nothing we need to know there, isolated from sewage, doesn't matter where it came from, okay, produced 23 milliliters. Oh, what's 23 milliliters? A volume. Most likely an initial state. I'm going to assume it's initial state unless the problem tells me later and I have to change the numbers. But 23 milliliters, 23.0 milliliters is a volume. I'm going to assume that's my initial volume. Produced 23 milliliters of methane gas. I don't really care that it's CH4. At 23 degrees Celsius. And 795 torr. What would the volume of the methane be at STP? Now, I recognize that for the lecture and class we've had up to this point, you have not, unless you've read ahead, which hopefully you have, but you may not have yet encountered the term STP. But on page 395, which is the next page after we stop the lecture, it talks about STP, standard temperature pressure. What is standard temperature and pressure? It's just something you have to memorize. It's blue, it's a definition. Standard temp and pressure is 273 degrees Kelvin and and pressure is at 1 atmosphere. Okay. So from this initial state, what would the volume be at STP, at standard temperature pressure? So I've got a few options here, don't I? Other than writing out the formula, so you look at the variables, the knowns and the unknowns, what are some things that we have to do first? Yes? Okay, temperatures have to be in Kelvin to use the formulas we're using. So we have to convert 23 degrees Celsius into Kelvin. Now, how far can I take it out? When we're adding numbers, what's the rule with precision and significant figures?
Is the 2 of them? First two?
Okay, let's do the rule first. Okay. The rule is for addition and subtraction, your answer can only be as precise as the least precise, right? Which of these is, what's the degree of precision with the least precision? Pardon? The 10th place. This is the least precise. This one is more precise. Remember, precision is based upon the number of places after the decimal point, the number of places. Okay, so this is the least precise to the 10th place. So my answer here can only go to the 10th place. So when I add this up, I technically get 296.15, but I can't take it to the 15. I can only take it to the 10th place, which would be 1, but it's followed by 5. So what's the rule? 5 or greater, round up. So 96.15 becomes 296.2. Okay? Because it can only go to the 10th place. Why? My least precise was to the 10th place. So it can only go to the 10th place. So 296.2 Kelvin. So I have the temperatures. They're both in Kelvin now. Volumes. I'm looking for the second volume. I've got the first volume. Pressures. Someone else. What do I need to do here? Say again? Okay, they can both be in atmospheres or both be in torr. Now, if I decide they're both going to be in torr, what is this going to equal over here? So 1 atmosphere is the same as 760 torr. If I decided I wanted to use atmospheres, how could I do it? I would need to convert 795 torr into atmospheres, right? I could do that by saying 795 torr times my unit conversion factor of 1 atmosphere is equal to 760 torr. When I do that math, it'll give me an answer in atmospheres. Okay? Torrs cancel torrs, and we're left with atmospheres. Simplest here is converting 1 atmosphere to 760 torr because you already have that memorized. So that's fine. That'll work. I just wanted to remind you on how we could do it. Since if you were solving for pressure and solve it in atmospheres, and your other pressure was not a perfect 1 atmosphere, how would you do it? This is converting torr to atmospheres by the factor of 1 over 760. All right, so we have our table of variables, knowns and unknowns. Now we need a formula. We did Boyle's law, we did Charles' law, and we did combined gas law. What's the beauty of the combined gas law? Charles and Boyle's are embedded in it. If you remember combined gas law, you have Boyle's in Charles' law. The combined gas law says P1V1 over T1 is equal to P2V2 over T2. Remember, if it's constant temperature, we can ignore the temperatures, which means it's just P1V1 equals P2V2, which is Boyle's law. If the pressure is constant, we ignore pressures, and we have V1 over T1 equals V2 over T2, which is Charles' law. Or considering all three variables, P1 V1 over T1 equals P2 V2 over T2. Next step from algebra 8th grade is rearrange this formula to solve for the unknown variable. The unknown variable, what we're solving for, is V2. So we need to take this equation and solve it for V2. V2 equals what? All right, so again, because this is pure multiplication and division, we can use the shortcut, which is to slide diagonally across the equal sign. Okay. So I'm solving for V2. If I keep that where it is and get rid of everything else, I can slide through the equal sign diagonally like that. So it becomes P1 V1 T2 all over T1 P2. For those of you that want to see the long process on how we did that, rather than just using the visual shortcut of sliding through the diagonally through the equal sign, okay, I want to get V2 by itself. So I need to get rid of P2 and T2. How do I do it? Well, if I multiply both sides by T2, T2 cancels T2, and it becomes P1 V1 T2 over T1 equals P2 V2. Okay, and then I say, wait a minute, I want V2 by itself, not good enough. Okay, so I'll divide both sides by P2. P2 cancels P2, and guess what I'm left with? V2 is equal to P1 V1 T2 over T1 P2. So just to rearrange it algebraically, whether you have to go through the long process or whether you remember pure multiplication division sliding through the diagonal, through the equal sign, I come up with this rearranged formula for the second volume. Then all I do is take the variables and plug them in. So V2 equals, well, P1 is 795. I'm going to keep all my units and put them at the end. 795 torr. V1, 23.0 milliliters. T2, 273 Kelvin, all over T1, 296.2, P2, 760 torr. Then I go through and cancel my units. Torr cancels torr, Kelvin cancels Kelvin. I'm left with milliliters. So whatever this is, it's going to solve for a volume. Am I looking for a volume? Yes, I am. Do the math. So the math involved in this, for those of you that are going, oh, math! The math is addition, okay, and multiplication. That's it. Addition and multiplication. You might argue division, but division is what? Inverse multiplication. And if we had subtraction, that is inverse addition. So arguably this is addition and multiplication. Conceptually, what's difficult? You might have difficulty rearrange the formula. But again, for juniors in high school, this should be pretty straightforward, almost intuitive. Okay, if it's not, I encourage you to keep working it. If you need extra help with algebra, please speak up. Everything we've done in this course so far has really just been multiplication, division, addition, and subtraction. We haven't had to do any derivatives. We haven't done any integrating. We haven't done anything, even using imaginary numbers. Though I enjoyed teaching imaginary numbers over in algebra, Algebra 2, this course doesn't go that deep in math. Physics, you would get into the imaginary numbers. For those of you who take physics next year, remember, we do a non-calculus based physics. So it's like baby physics, like, but that's where you're not at the calculus level for math yet. So that's why we do that. Okay. So any questions on the setup? Any questions on the process? Any questions on if I said use atmospheres to convert 795 torr into atmospheres? Question for you. Is this more or less than 1 atmosphere? More. So when I convert it, I'm going to divide this by 760, right? Which is going to give me, well, it would be 1 and a remainder of 35 over 760. So you'd have 1 and a small fractional portion, a small decimal portion after that. So just so you could ballpark it. So if I set up there and says, this is a little bit more than 1 atmosphere, and here's 1 atmosphere, so it's a decreasing pressure. See? You can make that kind of assumption just by knowing that that's a little bit more than 1 atmosphere. If I have a decreasing pressure, but then we got temperature into it as well. If we had a constant temperature, then I could make some statement about, well, if I am just looking at volume and pressure, and I've got a decreasing pressure, I must have an increasing volume at a constant temperature. So then you would know your answer should be greater. See? Things like that. All right, let me clear the board for number 2. We'll press on to number 3. Okay, number 3. It's probably a gas law problem, or gas question, right? So, probably going to need to know now look at the text. A steel container with a volume that cannot change is filled with 95.0 atmospheres of compressed air at 20 degrees Celsius. And they give us just to that it sits out in the sun all day and turns into tomato. No, it sits in the sun all day and the temperature rises to 55 degrees Celsius. What's the new pressure? Okay, so we have your table of variables. We needed to use that equation already to solve these for Kelvin because they were given in Celsius. And we have our combined gas law equation. We're asked to solve for P2. So we need to rearrange the formula to solve for P2. Again, if I use a shortcut through the diagonals, P2 is equal to P1 V1 T2 all over T1 P V2. Okay. The volumes are the same. Pressures what I'm looking for. I've got the temperatures. Now, since the volumes are the same, what could I have done? What can I do now, even? The volumes are the same, so they're gonna be equal, which means they cancel each other out, right? So P2 becomes P1 T2 over T1. Now, some of you like to put the numbers in there and start sliding the numbers around. I prefer to use the variables until I've got the equation set, completely done, and then plug in the numbers. So P2 is equal to P1, 95.0 atmospheres, T2, 328 Kelvin, divided by T1, 293 Kelvin. Kelvin cancels Kelvin. I'm left with atmospheres. It's a pressure. I'm solving for pressure. My setup is right. My pressure should be in the same units as my initial units, atmospheres. Okay. So then I do the math. 328 divided by 293 times 95. Your answer is going to be, well, 328 over 295. It's going to be 1 and about 35 over 295. So it's about 1 and a sixth. So 1 and a sixth times this. It should be somewhere around what? 1/6 of that's about 15, so it's going to be somewhere around 110. $106. So 106 atmospheres is the answer the book has. Okay? But again, nothing new. Same process you're going to follow. Table of variables, equation, rearrange for the unknown variable you're solving for, plug in the numbers, check your units, do the math. And now we go to the back of the book. Right? Is that 2 and 3 were the 2 practice problems? Let's go ahead and take a look quickly at extra practice problems 1, 2, and 3. Let's see. Don't necessarily need that one yet, but we will soon. So again, that's what I'd write in my paper even before I read the problem if I knew it was a gas problem. There are a couple other formulas as we finish the module that you probably go ahead and write down and not use, but it's pretty quick. You get Dalton's law of partial pressures, a restatement of partial pressures as mole fractions, and I think that's pretty much most of it. So now actually looking at the problem and pulling stuff out. A balloon is filled with air so that the volume is 11.2 liters. At 25 degrees Celsius. It is then lowered into a vat of liquid nitrogen so that it reaches a temperature of negative 196 Celsius. Assuming the pressure stays constant, What's the new volume? Okay. First step, what do we need to do? Convert the Kelvins, right? Pressures don't matter. My volume I solve for, if I just plug it in, it's going to be in liters, but I do need to convert to Kelvin. So I double check because sometimes I drop the zero. I did? Good. So it's 25.0 degrees Celsius. Does that matter? (196) and 196.0. They're not the same number, obviously. Is it significant? Yes, it is. In math, it may not be, but in chemistry, it is, because now, when I convert to Kelvin, I'm going to be able to write it to the tenths place instead of the ones place. So the 0.0 matters. What does it mean that I have a 25.0 and not simply a 25? It meant that I had a thermometer that was actually marked out to the ones place so I could estimate the tenths place. Or rather, to the tenths place, and I could estimate out to the hundredths place, to round to the tenths place. So remember, the precision is based upon how precise, usually how expensive your tool is for measuring that variable. So I need to convert both of these to Kelvin. So T1 is equal to 273.15 plus 25.0, which equals 298.2. Right, because I can take it to the tenths place. Negative 196, so it's 273.15 minus 196.0, or add 77.2. Okay. Since the pressures is constant, I can remove it from the equation. I'm solving for V2. Becomes V1 T2 over T1 11.2 times 77.2 divided by 298.2, because this is in liters. Kelvin, Kelvin, Kelvin cancels Kelvin. My answer is in liters. It's a volume, that's what I'm solving for. And then I do the math. Roughly speaking, what is this going to be? Just estimate it real quick. What's this going to be about? Approximately, what's the answer? Let's relate the 77 to 298, okay? How many times does 77 go into 298? Approximately. 4 times? About 4 times? If it was 80, 4 times would be 320. If it's 75, 4 times is 300. See? So it's going to be a little less than a quarter, 1 over 4. So it's going to be a little less than a quarter. So your answer is going to be a little less than a quarter of that. A quarter of that would be a little less than 3. So it's a little less than 3. .9 is the answer. Okay. So you could be over there making dirt pie or whatever that's called, or you could be doing chemistry. I mean, which is more fun? You're lucky. Any questions? Any questions on setup or process? I'm sorry, I know it's not fair that I get to have all this fun up here. You guys just have to sit there and watch. But I offered to give you fun, right? Anybody want to do problem number 2? I haven't even looked at it yet. It could be awesome fun. Maybe I'll do the bouquet thing. I'll throw it over my shoulder, and whoever is closest to it gets to come up and do it. Okay, EPP 11.2. It's probably a gas problem again. Boring. P2, V2, T2. Don't you get tired of seeing the same type of problem over and over and over again, and then getting it wrong on the test anyway? Isn't it amazing how that works? I'm so bored, but I can't do it. Okay. A balloon is filled with helium. Okay. Yes. You'll do it? Come on up. Want me to read it to you? Thank you, ma'am. All right, a taker. So I'll read the problem. Go ahead and do it. So a balloon is filled with helium at a temperature of 25 degrees Celsius and a pressure of 755 millimeters of mercury, so that its volume is 13.3 liters. Use a capital L for liters on V1. Yeah. It then rises. So now we're going to the second state. It then rises to an altitude where the temperature is 15 degrees Celsius, 15.0 degrees Celsius, and the pressure is 625 millimeters of mercury. What is the volume at that altitude? Good. Good catch. Thank you. Okay. Any questions? Any helpful critiques? This isn't criticism, okay? This is helpful critique. Something on here? Good catch about you were initially putting it down in Celsius, then catching that had to be in Kelvin, going back and erasing the 15 and replacing with 288.2. Good catch there. I'm not going to get technical about adding Celsius and Kelvin, but you see the process, how she ended up with the right answers here, both in Kelvin. One thing I'd like to encourage you on your notation is to make sure that you leave these all as subscripts. P1 V1 over T1, P2 V2 over T2. The subscript identifies it. The superscript is squaring it. So you will, as you go on in math, if you see this, you will tend to look down here then and go, okay, so why isn't this squared? Well, you've got two cases, and that hopefully would draw you, wait a minute, that's the second case, and you go back and fix it. But you could see on a rush, like you're sitting there in the ACTs and you're pressing through real fast, and you see a square in your own formula, you lead yourself astray by doing that. So keep them as subscripts, not superscripts. But other than that, table of variables, equation, rearranged for the unknown variable, plugged in, solved, checked units, saw that it was a volume, and then solved for V2. Very good. And the right answer. One more. EPP 3. And I tend to always put T at the bottom of my table of variables because that's the one we're going to have to do the addition. So I intentionally put it at the bottom so I can just add down, just so you know. So number 3 says a chemist collects 56.7 milliliters of nitrogen gas at 25 degrees Celsius. Is it 25.0? It is not. At 370 torr. What would be the volume of the nitrogen? At STP. Actually, it's not degrees, it's just 273 Kelvin. And what's my pressure going to be? It's standard temperature pressure. Could write it several ways, right? I could be 1 atmosphere, or 760 millimeters of mercury, or 760 torr, or 101.3 kilopascals. But since we're at torr, we want to go ahead and write it in the same pressure units. So we're going to write this as 760 torr. Make sure we've got consistent units. They're the same. We'll solve it in milliliters, and we need to be in Kelvin. That one is, this one's not. Okay, so it's 298 Kelvin. Solving for V2. Plugging in the numbers. So this is torr, 56.7 milliliters, Kelvin, all over 298 Kelvin, torr. Okay. Milliliters, solving for volume, milliliters, do the math. In this case, 56, book says 25 milliliters. Why is it 25 milliliters? We've got multiplication and division going on here, right? Why isn't it 25.0 milliliters or 25.00 milliliters? Let's look at it real quickly, right? Yes? No, coming back over here, look at these actual numbers that I've got plugged in. Multiplication, division, your answer can only have as many significant figures as the one that has the least significant figures, right? How many significant figures are in 370? 2. Which is why the answer is 25 milliliters to 2 significant figures. You might be able on your calculator to give me an answer that has more decimal places than that, but that doesn't make it more accurate.